there is a really strong presence here in the meeting for a lot of the things that we do in practice and a lot of things that are changing in our practice now. And one of the things I think that is changing a lot is the use of neuromodulation and especially spinal cord stimulation. There's a great session tomorrow morning on it as well. One of the things I can give you kind of in the background is we've had spinal cord stimulation for a very long time. I mean, our epidural stimulation has been around since the 1950s, FDA approved in the 1980s. But for the longest time, we only had a couple papers that actually showed that it worked. And I want to take you back about 5 to 6 years ago. Neuromodulation was about a $1 billion healthcare expenditure. Fast forward 5 years now, we're over $5 billion, and they think by mid-2020 we will be a $20 billion healthcare expenditure. That is how fast neuromodulation is growing, and especially spinal cord stimulation. And I think the reason that that's happening is one is the science has changed tremendously, innovation is changing, but we're also acquiring a lot of data to show that what we do works. And I think what we're doing now is we're taking a step back and we're starting to try to understand what we're doing, understand the mechanism of action. And then basically, I think we're going to get to the point in the next 5 years that we are going to completely objectify pain relief with a stimulator. We are going to know on the table who's actually going to respond to a stimulator, exactly what parameters to stimulate them at, and where to place the lead. And I'm going to hopefully paint that picture for you now. They already showed my disclosures. Now, a lot of this is based on, I'm not sure if everyone's familiar with intraoperative neuromonitoring. So there's two ways to place stimulators. You either keep the patient awake, you keep them awake for both the safety aspect and to confirm that the lead was in the right location so you can do paresthesia mapping. Well, in about the 2006, 2007, there was a kind of movement that was happening with surgeons where we were putting the patients asleep, but then we lost our safety aspect, and then we lost the ability to test where the lead was. So we started using intraoperative neuromonitoring. I'm going to show you some of the papers that came out for it. My goal of the talk is actually not to prove to you to use intraoperative neuromonitoring. I'm just giving you a little background on it because we started using the science from intraoperative neuromonitoring. We actually started recording real human nerves in the operating room to determine the mechanism of action of spinal cord stim. The mechanism of action of spinal cord stim is not known. If you look at all the papers talking about how spinal cord stim works, how tonic stim works, how all the new waveform works, it's all based on computer modeling and animal models. There's never been a single study that's recorded a real human nerve with spinal cord stimulation until now. The NAC guidelines, I'm not sure if everyone's familiar with it, the Neuromodulation Appropriate Consensus Committee is a committee of about 30 international physicians who every 2 years update the guidelines for neuromodulation. Everything from, do you use antibiotics? Do you stop aspirin? And what was interesting, and I think this was really a point and an inflection point for us, was in the 2016 update, they put this in the update, which basically said there is only two ways to place a spinal cord stimulator. They are either completely awake, or if they are sedated or asleep, you have to use intraoperative neuromonitoring, and there's not an in-between point. So the idea is the days of when we used to sedate patients and put up leads and you lose your safety aspect, one of the whole reasons you're keeping them awake is what the guidelines are saying you shouldn't do. And I think this was a big inflection point for us. This is just a little bit of background on neuromonitoring. Surgeons have used it since the 60s and 70s for scoliosis surgery. There's the two aspects of it. One is the safety aspect, so we can monitor sensory signals and motor signals, but then the more important aspect for spinal cord stim is confirming that the lead's in the right location. We know, based on a lot of studies, especially by work by Holsheimer, 40% of the time, your spinal cord is not in the midline. So that means if you put an electrode on anatomic midline on an x-ray, 40% of the time you will not generate proper coverage. There was a great paper out of Harvard from Dr. Jeff Arley. He put a 5-column paddle electrode on anatomic midline, didn't test. 20% of the time he could not generate bilateral coverage. So imagine that, 20% of the time with a 5-column paddle electrode placed on anatomic midline, you would not get proper physiological coverage of the spine. So this shows you that, one, it's important to either wake the patient up and test, or two, to use some kind of monitoring or intraoperative neuromonitoring to confirm. There's obviously some potential benefits to putting it in a sleep, patient comfort, physician comfort. I'll show you some of the studies that showed how well it worked. 2016, we actually started publishing the protocols. This is one of the protocols that I published so that I could spell out how to do it. To put this into perspective, one of the first papers that was ever written was in 2011. At that point in time, probably about 20% of surgeons were using intraoperative neuromonitoring for spinal cord stimulation. The latest surveys now that came out of NANS, as well as industry, show that about 50% of implanting surgeons use intraoperative neuromonitoring. But even more importantly, 20 to 30% of implanting interventional pain physicians use intraoperative neuromonitoring, which I think is the biggest growth for it right now. These were the two big pioneering papers. One was in 2011, a retrospective review, followed by in 2018, a multi-center prospective study directly comparing awake and asleep placement of stimulators with neuromonitoring. Now, like I said, the goal is not to tell you to use intraoperative neuromonitoring. It's just to give you a little bit of background, but to give a little bit of the results of that 2018 study that's published. Basically, what it showed in a direct comparison of awake versus asleep with neuromonitoring, in every single time scenario, it was 25% faster to do asleep with intraoperative neuromonitoring. It had a fifth of the adverse events, and it was nearly twice as accurate. So there's a lot of myths out there that intraoperative neuromonitoring is too expensive, it takes too long, and that it's really hard to implement. That study was done with both private centers, academic centers, residents, non-residents, with pain physicians, with surgeons. So to put that into perspective, you could bring a patient into an operating room, put them under general anesthesia, hook up neuromonitoring electrodes, and position the patient 25% faster than you can bring an awake patient into a room and get them ready for the procedure. That's what it actually showed. But like I said, this is not to prove, I'm very passionate about intraoperative neuromonitoring, but this is just to give you a little background on it. But this is the more important thing. So about 2 years ago, I was sitting in the operating room, and I was talking to my rep from one of the companies, and it's very rare, but sometimes we have a little bit of difficulty getting signals with the intraoperative neuromonitoring, and he said, well, why don't you just run our waveform under it? And I kind of looked at him, and I said, well, we always just do traditional tonic in the operating room. And it occurred to me, every single day, and I'm a high-volume practice, I record real human nerves in the operating room, sensory fibers, motor fibers, EMG, wide dynamic range neurons of the spinal cord. And I said, I could actually place every single company's waveforms and tonic stimulation under intraoperative neuromonitoring and see what would happen. And I could start elucidating how different waveforms actually work and whether some waveforms really do something different than other ones. So we put together this paper, single author, myself, non-industry funded, and I call it an observational study where I just basically spelled out what I saw and I didn't try to interpret what it meant. So to give you a little background of how this normally works, so we use what's called an H reflex, if you want to try to remember back to med school. So the way I think about it is when you touch a hot stove, you pull your hand back before you even realize it's hot. It's because you generate a sensory input that's so big, you get a motor contraction before your brain even realizes it. We turn up stimulation really high in the operating room and just try to get your motor fibers to contract. If I can get your quadricep to contract, I know that I'm putting paresthesias in the front of your thigh. We can use the amplitudes of the contractions to tell us how far left or right we are. We can use those myotomes as a marker for dermatomal coverage. That's how we use it. So what you see here is every different muscle group, starting with the abdominals to the iliopsoas, or your hips, your quads, your TA, and your feet. As we increase the stimulation, you get a one-to-one response and a one-to-one EMG signal, and it penetrates from superficial in the cord to deep. So you're going to, we're usually up around, say, T9, so you're going to get your abdominal fibers first, then you're going to get your hips, and then your quads, and eventually, if you turn the signal up high enough, you'll get really deep into the spinal cord to the feet. And what you see is it's a one-to-one response, and then we compare left and right, and we can determine if we're getting proper coverage and how far left or right we are. So this is traditional tonic stimulation. So this is interesting. There's a waveform on the market that has a 5-pulse sequence. It's a very specific 5-pulse sequence. When we put that sequence underneath the neuromonitoring, what you can see is the 5 pulses build up, kind of like a charge accumulation. Nothing's happening beneath it. There's no muscle responses. There's no fiber recruitment that happens. It's not till actually it comes back from a rest phase or like a passive discharge that you see the first response come through. What's interesting, though, is where do you see the first response? The deepest fibers in the spinal cord. So it's actually penetrating very deep in the spinal cord. This happens at 0.5 milliamps. To put that into perspective, when we run tonic stimulation, it's 8 to 10 milliamps. So at 0.5 milliamps, we were actually penetrating to the deepest levels of the spinal cord. And then what's also interesting, when I wrote this paper, I actually had to go back to the science books. Because when I looked at that action potential or that EMG activity, it was a very large compounded action potential. And I was trying to remember back to science high school class, and I said, wait a minute, an action potential is an action potential. It can't change. You can't compound it. It can't get bigger. You can't fire another one until that one goes away. Turns out, when I went back to the science books, there's only one place in the human body that you can compound an action potential, and it's the wide dynamic range neurons of your spinal cord. So it made sense. What's interesting with this sequence is as you turned it up higher, it started coming more and more superficial and running backwards. So then we did what was called cycling, or 3D burst modeling, it's been called as well, where you can take tonic stimulation and turn it on and off multiple times. And you usually have to turn it off after a certain amount of time. So this one's a 4-pulse sequence. You turn it off on the 5th one so you have an active discharge. And what it shows you, though, with that sequence is it acts just like tonic stimulation. So every single time you hit the cord, you get a signal that penetrates from superficial to deep. What was interesting, though, with the cycling is it was actually much more energy efficient. So this was running at about 2.5 to 4 milliamps as opposed to 8 milliamps that we would do in the operating room. So even though cycling or doing like a 3D burst like this acts like tonic stimulation, it's more energy efficient. Then we started playing around with different things like pulse width and frequency and what happens if you raise it up over 1,000 hertz and 1,500 hertz. What you actually start to see is the higher you raise the frequency, and once you cross over, it looks like about 1,500 hertz, you actually change the mechanism of action, and you no longer generate action potentials, you actually get inhibitory responses. So what ends up happening is what you see here is signals start dropping out. And what you're seeing on the top line is just nerve root irritation. Eventually, you even lose nerve root irritation. And what that showed us was we were inhibiting the signals that were coming into the spinal cord as opposed to activating fibers. So the idea of, say, 10,000 hertz would run by an inhibitory mechanism as opposed to an excitatory mechanism. This was interesting. So if you use on the top part of the screen, you put on tonic stimulation. That's tonic stimulation at 8 milliamps. So you turn that off, you put on the 5-pulse burst sequence, the one that runs at 0.5 milliamps, and you go back to tonic. That's now the same patient on tonic at 2 milliamps. So basically a fourth of the signal going in generated 4 times the amount of the response. So what it showed you was one of the waveforms, that 5-pulse sequence, was actually hyper-exciting the nerves and almost prepping them to listen to any signal that would come in at much lower thresholds. So this to me is obviously an exciting time because one is we're getting to the point where we can actually objectify what's happening in the spinal cord, and we can actually even hyper-excite nerves and lower thresholds. Imagine if we can start combining waveforms now. So say somebody has very high amplitudes on tonic stimulation, and one of the common things that happens with tonic stimulation is we can get back coverage on everyone, but we have to turn it up so high that their legs are wobbling. Well, what if we could hyper-excite the nerves first, drop the thresholds, and now give them tonic stimulation? So imagine all the things that we can start doing now by looking at how the mechanism of action affects these nerve fibers. This was actually quite interesting. This was an Italian study that also did intraoperative neuromonitoring, but they also did intracranial monitoring. And what they showed was that with that burst sequencing, that you actually inhibit the frontal lobes of the brain right there on the operating room table, as opposed to with traditional tonic parameters, you only inhibit the sensory cortex or the lateral pathways. So it's quite interesting to see that even with this now, you can actually see different mechanisms occurring right there on the operating room table. We're entering this era of closed-loop stimulation, which is this idea of feedback mechanisms where now you can actually stimulate the spinal cord, but then listen to the action potentials on the spinal cord. So it's not only now that we're blindly stimulating the nerves and see what happens, we'll actually try to generate what's come to be known as an ECAP, or an evoked compound action potential. But what's interesting about this now, this is actually, if you put this with all the waveforms and the tonic stimulation and what we're starting to understand, you're getting to a point where we can almost completely objectify pain relief. So in other words, if I can generate, I know that I'm in the operating room and I'm recording an ECAP. So in other words, I stimulate the spinal cord and then I record the spinal cord, and I can generate the most perfect ECAP, morphology, highest amplitudes, well, I know that that's going to be the perfect spot for you to generate pain relief. It's almost using a marker of an ECAP as pain relief. And because now we're starting to understand the mechanism of actions of how different waveforms work and the different parameters and how we're going to adjust those parameters, we can now record an ECAP and then adjust them accordingly to get the best ECAP. So we don't have to even have a subjectiveness to it where we ask the patient, well, where do you feel it? And can I go higher? Can I go lower? Well, if you tolerate a little more of this paresthesia, we can probably get better pain relief. Now we can clearly say, well, I generated the perfect ECAP in you, and this is going to be the best pain relief you're going to get. The problem is now is we don't know like what the best thing is for that patient. So it could be at the best programming parameters, we could probably get 70% pain relief for this patient. But we don't know that our max for that patient is going to be 70%. We're going to keep going for more, right? And then we may lose that. And all. By doing things like this and being able to measure ECAPs, understanding mechanisms like this, we can get to a point where we say, this is the most ideal situation that's going to be for you. And if it's 70% or 80%, we know that this is the perfect objectified pain relief for you. So what was interesting, though, is so I started now using the intraoperative neuromonitoring with the ECAPs, the ability to record action potentials in the operating room. So one of the downsides to doing intraoperative neuromonitoring is you have to put electrodes on the patient. You have to have a technician in the room that helps you interpret the signals. What if you didn't need any of that? What if you put a spinal cord lead in, you stimulate and record off the lead, and the lead tells us whether it's left or right and what fibers I'm actually activating. So we started doing research on this now with closed-loop systems. Oh, this isn't working. I'm not able to move ahead. You can just go to the next slide. So what we started doing was we had to figure out a way to correlate the signals that we saw with intraoperative neuromonitoring with what we were recording off the electrode. So there was a lot of, this has been years of work now where we got to the point where we had an ECAP, or the evoked compound action potential. But then what we did is, can you go back one slide? Okay, so what we did is we would get the ECAP, the action potential when you turn on the electrode. What we realized, though, is if we kept turning the stimulation up, eventually we got what's called this late response. So you get the first action potential, which is your ECAP, and you keep going up with the signal, you eventually get this other peak later on. So we called it a late response. What was interesting is that late response correlated one-to-one with the EMG activity we would get with the intraoperative neuromonitoring. So what we started doing was looking at the ratios of, okay, I generate ECAP, I generate a late response. The late response correlates with the activity of being left or right. Well, what ratio means you're in the midline? What ratio tells you you're too far? Thank you. So what this shows is, let me see if I got this right. So if you look on the right there, we're increasing the amplitude. You keep going up, you eventually get an ECAP. Keep going up, your ECAP gets bigger. Keep going up, your ECAP gets to now what's considered a peak ECAP, so it's the perfect ECAP, and then you start getting this late response. Based on that ratio, which we figured out is about 1.5, that will tell you that you're on the midline. If the ratio goes the other way, so imagine the late response is your EMG, it's the nerve root. If you're going up with your signal, and the first thing you see is your late response, you're closer to the nerve root on one side than you are to the midline on the spinal cord. So now we've gotten to a point that not only can we objectify that we're getting the perfect ECAP, I can tell you how far left or right I am and whether or not I'm getting perfect coverage bilateral. And then you combine that with the EMG activity and you know exactly what nerve fibers you're recruiting. The great thing about this is, we showed in the paper looking at a sleep placement with neuromonitoring, we do this in less than 2 minutes in the operating room. So no waking patients up, no taking the time to wait for anything. As soon as I put the lead in, we hook up and in 2 minutes I have all these signals fed back to me. This was just looking at the results of that paper. We've actually published 2 of them on it now. Just even looking at a percutaneous lead and how we have these small arching or twisting of the lead at the top, which helps you steer. What we actually saw just on the same lead on the top contact, the ratios would drop off because just that little top part of the contact was getting closer to the nerve root, and we could see the drop off in the ratios. That's how sensitive this is becoming. This also looked at, everyone's familiar now with DRG stimulation or dorsal root ganglion stimulation. So we started writing protocols to place dorsal root ganglion stimulators under intraoperative neuromonitoring. But we took it even a step further. So we developed the protocols to actually determine that you're dorsal in the foramen and not ventral. But then we started looking at protocols to actually map out where the DRG is so that you can perfectly place the electrode, even down, and which I think is the most interesting, is that even down at S1, which there's all this debate about whether it's in the canal, transforaminal, how far do you have to place these 4 contacts into the foramen versus the canal. We were able actually to measure and map out exactly where the DRG is within 30 seconds. It turns out that about 90% of the time it's in the canal. It's only about 10% of the time entering into the foramen, but it's never actually distal to the foramen. So we determined, and the papers was just accepted for publication in the Journal of Neuromodulation, that at the most you just want to put 1 contact into the foramen and keep the other 3 in the canal, because it's going to give you the best chance of stimulating the DRG.